Welcome back. I'm going to try and go over a bunch of these electric field questions and hopefully it helps. Let's get right to it. So I'll just do the first one quick. It's got a micro in there, just to remind you, micro means 10 to the minus 6. Pretty simple one. We want to know the magnitude of the electric field strength. We got distance and we got charge, so we can use our point charge formula. Your electric field strength equals KQ over R squared. By the way, these straight lines right here, they indicate that gives you the magnitude, the magnitude of the electric field strength. It doesn't tell you the direction. You'll have to look that through for yourself to figure that out. Anyway, so that'd be 9 times 10 to the 9 times 8 times 10 to the minus 6 coulombs all over 7.5 times 10 to the minus 1 or 0.75 all squared. That's it. That's all you got to do. On to the next guy. Next one I wanted to mention was number 7, skipping way ahead. This one involves an alpha particle and has sort of a tricky piece to it. So let's do it. So first thing we'd like to do, we've got the electric field strength, we'd like to find the force. Now, remember electric field strength is defined as force per charge. And so we could just find force. Force is just going to be your newtons per coulomb times your coulombs, your electric field strength times your charge. So our electric field strength is given to us, so that would be 7.6 times 10 to the 4. And then our charge, it's an alpha particle. And if you've watched the previous videos, an alpha particle is composed of 2 protons and 2 neutrons. If we do this, we will find out that we've got 2 protons, and so our charge is 2 times the elementary charge. Elementary charge is in your data pages. It's the positive charge if you got a proton, negative charge if you got an electron. So our total charge here is 2 times, because we've got 2 protons, times your elementary charge, 1.6 times 10 to the minus 19 coulombs. Plug that in, we'll get our force. I'm not going to figure that out right now, but at that point you want to find acceleration, but you'll have to draw from a previous unit. Just F net equals MA. Actually, maybe I'll move that over here. We'll go into number 8. We're still working on number 7 because we want to find the initial acceleration. So whatever we get from here, that's going to be our F net. And then our mass is going to be 4 times the mass of a proton, or the mass of 2 times the mass of a proton plus 2 times the mass of a neutron. They're pretty darn similar. So 4 times the mass of a proton is fine. So I'm going to write it down there. 4 times 1.67 times 10 to the negative 27 is the mass of a proton, I believe. So this would be the mass of this alpha particle, composed of 4 protons and neutrons, which weigh roughly the same. So if we rearrange that, our acceleration is equal to our net force, which we got up here. Maybe I'll write Fe for electric force, and then divided by our mass, which is 4 times 1.67 times 10 to the negative 27. And that'll give you your answer. Just make sure you get your results from your first question and plug them in there. So that's number 7. Let's try number 9. Big one I wanted to draw attention to here was the whole alpha particle, because it comes up. So you need to know, hey, charge is 2 times the elementary charge, and mass is 4 times the mass of a proton, or 2 times the mass of a proton plus 2 times the mass of a neutron. I think mass of a neutron is 1.68 times 10 to the negative 27, so it makes a very small difference. All right, we will calculate the magnitude of the electric field strength midway between a 3 microcoulomb point charge and a 6 microcoulomb point charge if the objects are 8 times 10 to the minus 1 meters apart. So it really helps to draw these guys out. So we've got two positive charges, let's say, I'll write this, and let's say a 3 microcoulomb charge. And then let's say we got a bigger charge over here, let's say 6 microcoulomb charge. Now distance between them is this guy right here. And so the distance from the center point to either one will be half of that. So this would be 4 times 10 to the minus 1, or 0.1 or 0.4 meters. I'll just write this as 0.4 meters. 4 meters. All right, so now basically, you know how we did big minus small in the forces unit? We're going to do essentially the same thing here. Big electric field minus small electric field. Remember, the direction of the electric field is the direction a positive charge would be pushed. And so this guy would be trying to push a positive charge here to the left. This guy would be trying to push a positive charge here to the right. Electric field strength, like force, is a vector, and so they'll cancel out at lunch. It's symmetrical, so we could totally basically subtract. I'll do the full big minus small just to show you, but you could totally change this. An equivalent formula would be kind of like, an equivalent situation would be 3 microcoulombs, because 3 microcoulombs would cancel with 3 microcoulombs since they're the same distance away and kind of fighting each other, and 0.4. So you could just do KQ over 0.4 squared with this as your Q, and you'll get the same answer. But with the big minus small formula, so I'll say your net electric field equals your big electric field minus your small electric field. And so that would be K times 6 microcoulombs, or maybe I'll put in times 10 to the minus 6 times 10 to the minus 6 all over 0.4 squared. That's your left electric field because of this guy. And then we will also subtract K, 3 microcoulombs over 0.4 squared. And if you think about it, the results of this will totally end up being the same as K, 3 microcoulombs over 0.4 squared to the left. Yeah. Solve that, and that's how you do that guy. Don't be afraid to do a big minus small with this, and sometimes you have to build a triangle with Pythagoras if you got vertical and horizontal going on. All right, last one I want to do is this guy, and I'll just roughly go over it. So you want to find the magnitude of the electric field strength at a point in space where an electron experiences an initial acceleration of 7.5 times 10 to the 12 meters per second squared of acceleration. First thing we should probably do, it's basically the same kind of idea as the alpha particle one we did, except in reverse. Right now we've got the acceleration, and we're interested in the electric field strength, so we're going to use the acceleration to figure out the net force on the electron, and then plug it into this formula, and then solve for electric field strength. So same thing in reverse. Let's give it a go. So F net just equals m times a. I believe if you check your data pages, it's something like, very quickly, 9.11 times 10 to the minus 30. Yeah, 9.11 times 10 to the minus 31. There we are, would have been off. So our mass is 9.11 times 10 to the minus 31 times the acceleration we got, which is ridiculous, by the way. That will get you going well, if it could, without relativity involved, that would be speed of light in less than a second. But of course, relativity would have a very large factor very quickly. And then we'll get our net force, so whatever this happens to be, that'll be our net force. And then we can just plug it into the electric field strength equation. So your electric field strength is just equal to your newtons divided by your coulombs, and then you get newtons per coulomb. In this case, our force is whatever the heck we figured out here. And our charge is just the elementary charge because it's an electron. Don't bother making it negative because you don't know what direction it's going anyway. If it did say like, hey, it had an initial acceleration up, then it would be fine to put in negative, because a negative electric field up would be a positive electric field down. So then it would be useful, but it doesn't even give us the direction of the initial acceleration, so there's no point in putting it in negative. All right, our charge is the negative elementary charge, but we're getting rid of the negative, so just 1.6 times 10 to the negative 19. And that would be your answer. All right, happy studying and be well. Thanks for listening.